You are presented with this problem. Find all the zeros of the function f of x equals 6x cubed minus 23x squared minus 33x minus 10. Enter the zeros separated by commas. So at this point, we've learned how to divide polynomials, and we've learned how to use and when we can use synthetic division as a faster way to divide polynomials. As a reminder, that's when I have an integer as my root or my zero, which means it comes from a factor that looks like this, where k is an element of the integers, not the z, integers. Okay? It doesn't have to be, but it gets more complicated after that, so we're just going to stick with that. If folks want to expound on that outside of the video, go ahead and do that. One of the things I want to do now is I want to try a number that could possibly be a root or a zero of this polynomial. And the problem with that is my probability of guessing that correctly is close to 0. Why is it close to 0? Because I have no idea where to even begin. The possible zeros right now there are infinitely many. It's the whole x-axis, every single value on the x-axis, whether it be square root of 2, 17, 1/17, -3, 50 whatever. It's just too many numbers. Rene Descartes came up with through his work, he used this notation, I believe. Again, as I've said, I don't often look any of these original stuff up, so I don't know. Maybe he didn't use those letters. But in almost every text I've ever read, we use a p and a q. The p is assigned to the constant, and the q is assigned to the lead coefficient. And many of my students start referring to this as p's over q's, because what we want to do is we want to find all the factors of p. And so the factors of -10 are plus or minus 1 paired with plus or minus 10, because 1 times -10 is -10, and -1 times positive 10 is -10. And then I can also factor 10 into 2 and 5 for these combinations, plus 2 and -5, but then also -2 and positive 5. So those 8 numbers are the factors of -10. And we then take also q and find all the factors of the lead coefficient. Plus or minus 1 times plus or minus 6, and plus or minus 2 pairs with the plus or minus 3 in some way. 2 multiplied to become 6. And then Descartes told us we need to find all the possible combinations of those 8 p's divided by those 8 q's. So let me describe this. This is the long, you will never see me do this again. Positive 1 divided by positive 1, positive 1 divided by -1, -1 divided by positive 1, and -1 divided by -1. That's all the combinations of those two 1s over those two 1s, right? 2 and 2, combinations 4. So there's redundancy though. Isn't this positive 1? Isn't that positive 1? And isn't this -1 and -1? So we just get plus or minus 1. I'm going to do this one time so we can move faster through all the other combinations. So I get plus or minus 1 from this over that. Now I take the 2's over the 1's. I get plus or minus 2, right? Because anything divided by 1 is going to be the same. So I'm just going to get that first list again. Now I have to do all 8 of these divided by plus or minus 2. And what do I get? Plus or minus 1 over 2, plus or minus 2 over 2, but 2 over 2 is 1, and we already have plus or minus 1 right there. So plus or minus 5 over 2, and plus or minus 10 over 2. But 10 divided by 2 is 5. We have that right there. So plus or minus 5 is redundant. Now I take all of these and divide it by plus or minus 3. Plus or minus 1/3, plus or minus 2/3, plus or minus 5/3. Let's make a slightly better 5. Okay, maybe not. There we go. and then plus or minus 10/3. That's good. Now, all of those factors divided by plus or minus 6. Plus or minus 1/6, not redundant. Plus or minus 2/6, certainly redundant because that's 1/3. Plus or minus 3/6, that's redundant because, I'm sorry, 3/6. Where am I getting 3/6? 5/6, I know where I was getting it. Plus or minus 5/6, and then plus or minus 10/6. But 10/6 is 5/3, which is just above it. So those are possible rational zeros or possible rational roots. I've taken a list of infinitely many numbers and boiled it down to 24. There are 24 numbers here. Okay? Now, from that list, I choose. If I choose integers, I can use synthetic division. And so let's try 1. I'm going to write the coefficients of my polynomial. 6, negative 23, negative 33, and negative 10. And I'm going to divide. I'm going to bring down the 6. I'm going to multiply that 1 times the 6. And add those two numbers, and I get negative 17. I'm going to take this 1, multiply it times the negative 17, and get negative 17. Negative 17 and negative 33 is negative 50. And because I add those two numbers, and I get, and now I take this 1, multiply it times negative 50, get negative 50, add those two numbers, and I get negative 60. For 1 to be a root or a 0, negative 60 should be 0. That location should end up being a 0. Didn't work. So 1 is not a root or a 0. Now, I would have to try all the other numbers until one of them actually works. I happen to know which ones work because I looked it up ahead of time. So we're going to just jump to it. Yes, could we have a tedious 2 and then not 3, but negative 1, negative 2, and do all those? Yes, we could. There is a little bit of a shortcut. My students will get that. I'm not sure what the other instructors are going to be doing. I'm going to go right to it. 5 is going to work. 6, negative 23, negative 33, negative 10. So 5 times 6 is 30. 30 minus 23 is 7, because remember we're adding this. 5 times 7 is 35. Remember we're adding. So 35 minus 33 is 2. And then lastly, 5 times 2 is 10, and 10 minus 10 is 0, and it works. What this tells us is that we have a root, or 0, of 5, which means my factor was x minus 5, and my quotient is 6x squared plus 7x plus 2. And all of that multiplied together is our original polynomial. That's still f of x. It's just factored, like taking 72, like saying 72 is equal to 8 times 9, right? I factored out a 9. Okay? That's the analogy with just regular numbers, with just straight multiplication, not in polynomial multiplication. So now I have to find the other two. The other two are going to be in here. And here's the thing. We could continue on with long division or synthetic division. But the whole gist of it is I want to get, because if I start out with a quartic, an x to the 4th, or a quintic, an x to the 5th, I have to do this a whole bunch of times. Oh my goodness. But once I get to a quadratic, we have better tools than division to factor a quadratic. And even if it's not factorable, I can use the quadratic formula, which we're going to get to in other examples. Okay, so 6x squared plus 7x plus 2. I'm going to factor that. This requires factoring by grouping. If you know factoring by grouping, if you don't, here I'll try to explain it, not in detail, but I'm going to take the 6 and I'm going to multiply it times the 2, and I get 12. I almost said 30, my goodness. And if I take 12 and find the factors of 12, 1 times 6, I'm sorry, what the heck? 1 times 12, negative 1 times negative 12, 2 times 6, negative 2 times negative 6, 3 times 4, negative 3 times negative 4, and then I'm back, right? I'm back to 4, which is going to be repeating up the other side. So really what I have is I'm looking for the two numbers that add together to be 7, which is those two. And instead of writing them as constants in some binomial, right? If I wrote this is wrong, but plenty of students want to do this, right? They want to write this and go, yep, I'm all done, because that's the other, that works when this coefficient is 1. But when I'm factoring by grouping, it doesn't work, because watch, this will never become that. X times x, x squared. How do I get the 6? You can't. So that's not what this tells us to do. These two numbers inform us how to split the middle term. 6x squared, don't forget this, plus 3x plus 4x plus 2. These two numbers, this 3 and this 4, are telling me how to split the middle term. And now I'm going to group those two, and I'm going to group these two. I'm going to find the greatest common factor for those two pairs of terms. Now, I've emphasized, don't forget this. I left it out because I don't have any room over on the right. Now I do. I'm going to curl down a little bit. And I'm going to have 6x and 3x, 6x squared and 3x. So my greatest common factor is 3x. When I factor the 3x away from this, I'm left with 2x plus 1. And then I'm going to factor 2 from both of those terms. So plus 2. And I'm left with what? 2x plus 1. Factoring by grouping. And now I have this orange factor of my first term, and I have this orange factor of my second term, and they are the same. I'm going to factor the orange factor away from those two green factors in their respective terms. I'm going to copy down that because lots of students lose that. I'm going to factor this 2x plus 1 away from this 3x and that 2. And so when I divide that out, I'm left with 3x plus 2. So what are my 3 zeros, or what are my 3 roots? Oh, I've been explaining that with that whole thing up. Crappity crap. I'm going to have to do some editing. Okay, so what are my 3 factors? Remember, I take this, set it equal to 0. Take this separately, set it equal to 0. Set this separately equal to 0. And oops. And I get x equals 5. I get x equals negative 1/2. And I get x equals negative 2/3. And so those are our 3 answers. 5, comma, negative 1 divided by 2, comma, negative 2 divided by 3. Oops, what am I down there for? Because I didn't arrow out. Negative 2 divided by 3. Doink. Okay. Good luck.